Today's lesson is on 5-7, using the fundamental theorem of algebra. We've talked about this several times in class, so really you should feel like you know how to do most of this. That'll be kind of nice. So this is 5-7, day 1. Alright, our goal is to use the fundamental theorem to determine the number of zeros in a polynomial function. Alright, so basically what it means is that the degree of the polynomial is equal to the number of solutions. So we've talked about that many times in class. This was first proved in the 17 to 1800s. And so Carl Gauss, which is a really famous mathematician, super smart guy, figured this out in the 1800s. Alright, so going back to chapter 4 where we talked about complex numbers. So remember that you have the real part and the imaginary part. We dealt with this a little bit on Wednesday in class, so this should seem pretty familiar. Alright, so again, if we look at just kind of going back, and let's solve each of these polynomial equations. So grabbing all the prior knowledge, we're going to add 1 to both sides. 2x is equal to 1, divide by 2, x is equal to 1/2. So this guy has a degree of 1, and his solution is 1/2. Alright, so state how many solutions. So solutions are equal to 1. Classify each as rational, irrational, or imaginary. And because it's a fraction, it's rational. Alright? Letter B. I'm going to write that down. And then we're going to solve for x. So add 2 to both sides. Take the square root. So x is equal to plus or minus square root 2. So state how many solutions. There's 2 solutions. And if you look at the degree, it's 2. And then classify each as rational, irrational, or imaginary. So since the square root of 2 is not a perfect square, it's irrational. And then finally the third one. So we set it up to be able to solve using synthetic division. And I looked at the graph and found that 1 was one of the solutions. So bring down the 1, 1, 1, 1, 1, 0. So I end up with x squared plus x plus 1. So what two numbers multiply to make 1 and add to make 1? There aren't any. So we'll have to use our favorite quadratic equation. You could complete the square as well. It's just a little bit harder since 1 is odd. So b is negative 1 plus or minus the square root. B squared is 1 minus 4 times 1 times 1. Everybody's 1. So 2 times 1. So we have negative 1 plus or minus. We have square root of negative 3 over 2. So that's going to be negative 1 plus or minus I square root 3 over 2. So our solutions are the one that we found from the graph, or that I found from the graph, and then the negative 1 plus or minus I square root 3 all over 2. So this is 1, 2, 3 solutions. And if we look at the problem, it has a degree of 3. So there's 3 solutions, and we have 1 rational, the 1 because it's a whole number, and then we have 2 imaginary. Alright, so what we basically did was we just kind of explored the fundamental theorem of algebra. It just tells us that if the degree is 1, like in the first example, there's 1 solution. If the degree is 2, like in the second example, there was 2 solutions. If the degree is 3, like in the third example, there's 3 solutions. And the solutions could be real, pure imaginary, or complex. So what we just had were real, and then we also had the complex solutions, because we had the 1 plus square root of 3, or whatever it was, 1 plus or minus I square root 3, so that made it complex. Okay, so if we look at a problem like this, and I've already graphed them for you, so you don't have to take the time to graph them, we want to know how many solutions there are. So we're just looking to see how many times it touches the x-axis. So it touches once here, and it touches once here. All right, and you don't have to write this down, because it would be kind of hard for you to copy that down in your notes. But if we look at that, it actually only touches the graph twice. But if we look at the equation, there's actually supposed to be 3 solutions. So the answers are negative 1 and positive 1. So how come we don't see 3? The answer is because of this point here that I'm circling in blue. Whenever you have the line, the x-axis, and a graph touches the x-axis like this, where it's tangent to the x-axis, then that's called multiplicity. And there's actually two solutions at this one point. That's like what happens when you have like x plus 1 quantity squared. So I would have x plus 1 equals 0 and x plus 1 equals 0. Because squared means write it twice. And I'd have two solutions that are the same number. And that's what that looks like. It looks like where the graph is tangent to the x-axis. So anytime that happens, the -1 actually gets to count as two solutions. So I really have 1, 2, and then 3 solutions. So a little bit tricky on that one. All right, so again, just kind of explaining that whole idea of multiplicity. All right, so now solving using synthetic division in a graphing calculator. And sometimes, like in this problem, you won't be able to see the whole graph. This graph actually goes up and then comes back down at some point. We just don't see it because we don't see enough of the graph to know what's going on. So it's not actually a straight line and a parabola. It's a continuing motion. We just can't see all the parts of the graph. All right, so we look at the graph and we see that we have the number -4, which is a solution. So doing just like we did in class on Wednesday, we set up our synthetic division using the -4. Oops, sorry, that should be a positive one. And then this would be -4, -10, 40, 25, -100, and I have 0, right? So what I could do is see if it factors. Or, to make life even easier, if I use this next 0, it'll make the problem actually easier, right? Because now what was a cubic equation now becomes a quadratic equation. Well, let's just take the quadratic equation and reduce it again and make it a linear equation. So I'm going to use 1, 2, 3, 4, the 5. Bring this down, I have 1. Bring down and 5, so -5, -25. Now this is x, right? Because it was cubed, then it was a quadratic, and now it's linear. So now all I have is x minus 5 equals 0. How easy is that to solve? So our answers are -4, 5, and then 5 again, which I don't have to write twice. Right? And again, that's because there was multiplicity at this one point. Did I actually have to do all this work on the right? No, because I could have looked at the graph and seen that the solutions were -4 and then 5 twice. Right? But I did all the work because the directions said to use synthetic division. Alright, so let's look at this example. So we could graph it. I actually graphed it and found that it only touches at one point, -3. So that's going to be our starting point. We're going to start at -3. We're going to do 1, 3, 16, 48. Bring down the 1. So -3, 0, 0, 16, -48, and 0, right? And I didn't do the rationals, the P's and the Q's, because we already know how to do that, and I didn't want to waste your time here in the video. So that's why I didn't do any of that, just to make this go a little bit faster. But we will still do that in class. Alright, so now, I don't have any more zeros like I did in the problem before to take this quadratic equation and reduce it to a linear equation. So I'm just going to have to write it out and set it equal to 0. So, since we don't have any x's or anything, I can just minus 16 from both sides, take the square root, and x is equal to plus or minus 4i. So I have x is equal to the -3 we found in the beginning and plus or minus 4i. I knew that there was two imaginary solutions because the graph only touched the x-axis one time, and if you look up here, we know that there's 3 solutions. So now I have 1, 2, 3. All right, we're going to do these problems tomorrow in class. So if you're not going to be there, these are the problems that I want you to do. If you are going to be there, don't worry about it because we'll do them either on whiteboards or in our notebooks. All right, so see you guys then.